Okay, so the first half of calculus as you've studied is all about what's called derivatives. That's the slope of tangent lines and how we can apply those to real-world problems involving rates of change. The second half of calculus involves what are called antiderivatives and the fundamental theorem of calculus. So before we move on to the fundamental theorem of calculus, we're going to study what are called antiderivatives. So what is an antiderivative? Let's say we're given a function, f of x equals 2x. I want to know, is there a function, we'll call it capital F of x, such that its derivative is equal to 2x. So, since whatever this is, you have to take the derivative of to get f of x, little f of x, we call capital F of x the antiderivative. So what do you take the derivative of to get 2x? Well, that one you can pretty much think of in your head is x squared, because when you take the derivative of x squared, the 2 comes down and you get 2x. So we call this the antiderivative, because it's what you take the derivative of. Now, you have to be a little bit careful, because notice what I can do is I can add any constant here. So just as the derivative of x squared is 2x, it's also true that the derivative of x squared plus 100 is 2x. So when you're finding these antiderivatives, you have to be careful to always add a constant. So let's do another example. Let's say we want to find the antiderivative of f of x equals e to the x. So the question is, what do you take the derivative of to get e to the x? So we say the antiderivative is whatever you take the derivative of to get this. But what do you take the derivative of to get e to the x? E to the x. Nice simple function. But remember, always add a constant. So it would be nice if we had a symbol to say find the antiderivative, just like we have a symbol to say take the derivative. And we do. What we say is this symbol, which we call the integral, says find the antiderivative of f of x with respect to x. So if we break this down, this says find the derivative of f of x with respect to x. Just like this over here says take the derivative of f with respect to x. And we call this object an integral, or antiderivative. And so for the case of e to the x, that is e to the x plus c. So let's calculate a few more for practice. I want to know what is the integral of, let's say, sine of x. So what do we take the derivative of to get sine of x? Well, you may think cosine right off the bat because you're used to doing that for derivatives, but remember that when you take the derivative of cosine, you get a negative. So what it's going to be is negative cosine of x plus c. Okay, so let's do another one. What about this? So you might think at first it'll be 1 over x to some power, or maybe x to some power. But remember that when you take the derivative of the natural log, you get 1 over x. So we know this has to be a natural logarithm. But we have to be careful because you can't take the natural log of a negative number. So you have to throw that absolute value. Okay. So let's do one more example that might tend to trip you up the first time you do it. So remember that when you take derivatives, you always have to use the chain rule. Well, for antiderivatives, there are no nice rules that always work. The chain rule always works for derivatives, but there is no equivalent for antiderivatives. So what we have to do is basically we have to think backwards. So we have a 2 here, which usually means we have to multiply by 2 when using the chain rule. However, when we want the antiderivative, we have to divide by 2. But let's see why that works. Let's take the derivative of this side to make sure we get the right answer. So we take the derivative of this, so we get 1/2 cosine, leaving the inside alone, and then you have to multiply by the derivative of the inside. And then the derivative of constant is, of course, 0. So we see that the 2's, there's no x here. We see that the 2's cancel, and we get cosine of 2x, just like we wanted. Okay, so that is how you take an antiderivative. So now we're going to look at how these are useful and why we even needed to do this. Okay, so why did we need to learn about antiderivatives? Well, the reason is, recall that from previous lectures or previous classes you've had in calculus, that we calculated the area under a curve by looking at the sum of rectangles. We call this a Riemann sum. So let's say we wanted to find the area from some point A to B. Well, we called this area a sum of these rectangles, and the exact area, so if we wanted just the exact area under the curve, we took a limit. So we said limit as n approaches infinity of the sum k equals 1 to n f of xk delta x. And we said this was our area. But this is really hard to calculate for a lot of functions because it's kind of tricky to see what this sum goes to. But what we can do is we can employ what's called the fundamental theorem of calculus. Now, I'm not going to prove this here, but there are proofs all over the internet, and there will be a supplement to this video at some point that will have a proof contained in it. So what the fundamental theorem says is that when we want this sum, when we want this area, what it really equals is the antiderivative of f evaluated at the endpoints. And that's it. So that is the fundamental theorem of calculus. It says the area is just the antiderivative at b minus the antiderivative at a. So if you want to know the area of the inside, all you have to know is the behavior at the end, which is pretty cool. So how can we write this in a much better way than having to write out these Riemann sums every time? Well, what we can do is we can say the area is the antiderivative evaluated from a to b of f of x dx. So you kind of see where this notation comes from now, because basically this finite distance delta x becomes this infinitesimally small differential slice dx. So really, this antiderivative is a sum. So you can think of the integral as a sum of your functions adding over all of x. And that's what an integral really is. And so we write this as the antiderivative at b minus the antiderivative at a. We can also write this as the antiderivative, and then we use this notation, which means evaluate at b minus evaluated at a. So let's do an example of this, okay? Okay, let's say we wanted to find the area under the curve f of x equals 2x from 1 to 4. Now, you could do a Riemann sum, or you could just do this as, using triangles, because it's a fairly nice graph. Or we could use the fundamental theorem, which says that this object gives us the area under the curve. So we want to know the area from 1 to 4 of the graph 2x over x. So all we do is we find the antiderivative, which we've already established was x squared, and we evaluate from 1 to 4. So this gives us 4 squared minus 1 squared, which is 16 minus 1, which is 15. So what we have found is the area from here to there is equal to 15. So this fundamental theorem is extremely useful in finding areas. So it may not seem like a huge deal to find this area, But we can also use it to find areas of curves that we would normally have no idea how to find. So let's say we had the function f of x is x cubed from 1 to 2. There's no simple way to do that. There's no simple way to break that into triangles or trapezoids or anything else. But using our wonderful fundamental theorem, we can say that it's the area from 1 to 2 of our function x cubed. So what do we take the derivative of to get x cubed? Well, we know it's going to be an x to the fourth because the power comes down, but we also have to divide by the new power. Okay? And then we evaluate from 1 to 2. So we simply have 1/4, and then we have to multiply by 2 to the fourth minus 1. And that's simply our area. Okay, so now that we've seen how to do antiderivatives and how to do these integrals, which we evaluate on bounds, let's look at a slightly trickier example to get the other part of the fundamental theorem of calculus. Okay, so let's say I wanted to evaluate the integral from any constant a to x of some function. We'll call it a function of t. Could be time, doesn't matter, whatever parameterization you choose. And I want to take the derivative of that. All right, well, let's see how this works. Let's say that we know that the antiderivative of little f of x is capital F of x, or f of t. So what we can do by the fundamental theorem is say this is really the derivative of capital F of t evaluated from a to x, which is the derivative of capital F of x minus f of a. Notice, however, that f of a is a constant. It's just a function evaluated at a point. So its derivative is 0. So we're left with df dx. This is a function of x. And just by definition, that we've already assumed over here, this is little f of x. So this is the other part of the fundamental theorem. The derivative of the integral does in fact give you back your function. They undo each other basically. They're almost inverse functions of each other. You can think of it like that. So this is another reason we call it an antiderivative. We apply the derivative to the integral and get our function back. Notice also that you can say a similar statement when the derivative is in the inside of the integral. So if we were to say the integral of a derivative, let's say dy dx, they'll basically undo each other, and you'll get back y, plus a constant in this case, because it's an indefinite integral. If it doesn't have bounds, it's called indefinite. If it has bounds, it's called definite, because you have definite bounds. Let's look at this real quick. So why should this be true? Why should it be that you get just y when you integrate the derivative? Well, remember that, first off, the integral of dx is what you take the derivative of to get 1. So that's just x. Okay, so if you recall your chain rule, we can write the chain rule in a slightly, maybe different way than you've seen before, which says that dy dx is just equal to dy. And you can think of this almost as if it's acting like a fraction, because you have a dx and a dx here, so it looks like they should cancel. But you should really remember this rule. So from this, which is just the chain rule, we can say dy dx is the integral dy, which, when you take the derivative of to get y, or to get 1, y plus a constant. So that's why you can say this. Okay, and it doesn't matter what you're taking the integral with respect to. You can take it with respect to y, and you would do it just as if you took the integral with respect to x. You just have to switch your variables. So that is the fundamental theorem of calculus. This is one part, and then evaluating your integrals for areas is the other part. Okay, so let's do an example of this second part of the fundamental theorem that we went over. So let's just write the second part down real quick. Okay, so let's do an example where it's not so nice that you just integrate from a to x. Let's do just a general example real quick. What if I wanted to know the derivative from a constant to a function of f of t dt? Let's see how to work this out. So if we can work out this general problem, we can work out an example. So let's look at this. So let's again assume we know the antiderivative is capital F. Okay, so by the first part of the fundamental theorem, this is going to be the derivative of capital F of g of x minus capital F of a. So again, this part is simply 0 because the derivative of it is a derivative of a constant. So we're left with the derivative of capital F of g of x. Now you have to remember your chain rule here. We have a function, and then we have a composition of functions. So remember, this is the derivative of your outside function, leaving the inside alone, multiplying the derivative of the inside function. But we know that f prime is just lowercase f. So we have little f of g of x times g prime of x. Okay, so this may be a little obscure. So let's look at how we really would use this. So let's say we have the integral, or the derivative of the integral, from 1 sine of x of e to the minus x squared dx. Now, normally, if you ever solve this function, basically run and hide. It's a very difficult function to integrate, and can really only be done by hand if you're doing it from negative infinity to infinity. However, since we're doing the derivative of this to a function, what you need to do is just look at the fundamental theorem of calculus. So when we see this, we can immediately say, well, we don't know what the antiderivative of that is. It's really hard. But we can look at this and say that all it is this function evaluated at this function. So we have e to the minus sine squared of x. And then we just have to multiply by the derivative of this function. So times the derivative of sine of x. And that's it. We're done with the whole problem. There was no need to find antiderivatives. There was no need to actually calculate things out. That is simply the answer because we know the fundamental theorem of calculus. This is very useful for when you have to integrate to functions rather than numbers, which will be very useful in your calculus classes later on.